Okay, so today's lecture is talking about energy changes during phase changes and also some calculations associated with that. So it's basically an extension of yesterday's calculations. So up in the upper right-hand corner, I drew a picture of a phase change diagram and I highlighted a couple of segments. We are really going to be focusing in the first part of this lecture anyway about these portions of the phase change diagram, which, if you remember, this is where the phase change occurs. So like a solid would melt into a liquid, or a liquid would freeze into a solid, or a gas would condense into a liquid, and a liquid would evaporate into a gas. But during a phase change, all that energy is transferred into the reaction or out of the reaction, is used to cause the phase change. But it's not necessarily changing the temperature. So there's no thermal energy change. So what that means is that if water is going to melt at 0 degrees Celsius, or it's going to freeze at 0 degrees Celsius, the temperature will be maintained at 0 degrees Celsius until all of the liquid water has become a solid. At that point, then the temperature of the solid water, ice, could continue to go down. So we have a couple of things that we need to, phrases that we need to be familiar with. The heat of fusion is the amount of energy needed to melt 1 mole of a substance. So this is what we talk about when we go from a solid to a liquid. And this is generally considered positive in terms of a value, and a liquid to a solid would be a negative value usually. So then the next thing that we talk about is heat of vaporization. Again, amount of energy needed to convert 1 mole of liquid into a gas. So we would take liquid to gas, which again is a positive situation, and a gas to a liquid would be a negative situation. So how this all relates is to something that we call phase diagrams. And so this is a picture of a phase diagram. You may have seen this at some point before in your academic history, but there's a couple of things we need to identify on this graph that you need to be able to identify. First of all, across the bottom of a phase diagram is always temperature. Could be in Kelvin, could be in Celsius. I don't think you'll ever see one in Fahrenheit. And up the side is pressure. Those could be in ATM, millimeters mercury, kPa. So be aware of the unit of the pressure when you're asked to assess what's going on a phase diagram. Now, there are a bunch of places that we need to identify. First of all, solids generally occur in this area here, okay, and liquids generally occur in this area here, and gases generally occur underneath the entire curve. Now, think about it for a second in terms of what's going on in these instances. In terms of the gases, right, we appear to be at higher temperature but low pressure, so that allows us to be in the gas phase. The solids are at low temperature and pretty low pressure, so that also gets us into the solid phase. And then the liquids are kind of all over the place, but they're kind of in the middle, so that's kind of how we have to keep track of that stuff. Now, there's a bunch of things on here that we have to identify. They're labeled, and we'll talk about them individually. So we are going to start with let's see, something called the triple point. So I'm going to highlight this. The triple point is the space or the temperature and pressure on a graph where a pure substance will exist as a solid or a liquid or a gas at literally the same time. So this is when a pure substance exists as a solid, liquid, and gas at the same time. And again, the pressure and the temperature associated with the triple point is unique to every pure substance that we talk about. Another part of the graph that's going to become really important is the what do we call it? We call it the critical point or the critical temperature. So this here is, oops, let me do it this way. That is going to be my critical point. And my critical point is when a pure substance behaves as a liquid and a gas at the same time. And so that is an important part of the phase diagram for a pure substance. At both of these points, you cannot tell the phases apart. You just can't. So, which I realize is kind of a weird concept to think about. It's just they exist at either at the critical point as a solid or as a liquid and a gas, and at the triple point as a gas, a liquid, and a solid, literally at the same time. There are a couple other things that we need to be cognizant or aware of. So one of them is the, let's see, if I can get a different color here, that'd be great. We'll do this. So this is going to be our normal boiling point. And the normal boiling point is the temperature of a substance at which the substance boils at 1 atmosphere. So 1 ATM. So it's like 1 ATM or 760 millimeters of mercury or 101.325 kPa. That's where the normal boiling point occurs. The other point that we have to keep track of is what we call, in this case, would be the normal melting point. So the normal melting point is the temperature of a substance at which that substance melts at 1 atmosphere. So again, that would be 1 ATM or 760 millimeters of mercury of Hg. or 101.325 kPa. So those are the very important parts of a phase diagram. And one of your objects for homework tonight is going to be going to answer questions about what you see when you look at a phase diagram. So when we get back into the energy changes during phase changes, it's a different type of calculation. And the calculation is actually just simply stoichiometry. It's not hard, it's just a matter of putting it into place. So if I say how much energy is needed to melt 15 grams of ice, we're talking about the phase change. So we're talking technically about heat of fusion. Melting or solidifying is the heat of fusion. So when you're looking over at a chart that I give you, in this case, when I'm looking for melting, I'm going to be talking about the heat of fusion value. So it's a very simple stoichiometry calculation. I'm going to take the 15 grams of ice, which is water, and I need to convert it to moles, because remember the definition is the amount of energy required to melt 1 mole of that substance. So I know that in 1 mole of water, there's roughly, if I do the molar mass, it's 18.02 grams of water. And now I need to put in the calculation, or the value rather, for the heat of fusion. And in this case, the heat of fusion for ice is 6.01 kilojoules per mole. So I'm going to take the 6.01 kilojoules in 1 mole of water. So when I plug that into the calculator with sig figs and all the things that go along with it, I get a value somewhere around 5.00 kilojoules. So let's check that real quick, because I think that's right. 15 divided by 18.02 times 6.01. Yeah, it's like 5.0027 something or another. But that's in kilojoules. And the unit here is really quite important, as you'll see in the next example. So slide here. Specific heat of water when it's ice, solid, is 2.09 joules per gram per degree Celsius. And I'm going to see that the heat of fusion, remember solid to liquid, liquid to solid, is the 6.02 times 10, or 6.01 kilojoules. Back here real quick. And I'm going to see that liquid water here, its specific heat is 4.18 joules per gram per degree. So example number 2, it says how much energy is needed to change 100 grams of ice at negative 10 degrees Celsius to water at 25 degrees Celsius. So in my head, the way that I look at this is I have to draw a diagram because it helps me to see what's going on. So if we said that this is 0 degrees Celsius, right here we have ice, and then it's changing from ice into water or liquid, so it's going to go through a phase change, and then it's going to warm up from 0 to like 25 degrees Celsius. So here we're at negative 10, here we're at positive 25. Okay, so this tells me that there's going to be multiple steps for my problem here. And the first part of my problem tells me that I'm going to change, I have to bring the ice up from negative 10 to the freezing or melting point, which is 0 degrees Celsius. So calculation number 1 is going to be regular heat calculation like you had for homework last night. So Q would be equal to mass times specific heat times delta T. Okay, so I'm going to calculate the value of Q for 100 grams of ice. And the specific heat of water when it's ice, so I might have to go back to this. So I'm going to take the 2.09 joules per gram per degree Celsius, and I'm going to take the change in temperature. So this time it's TF minus TI. The initial was negative 10. The final is 0 degrees Celsius. So my final is 0 degrees Celsius minus negative 10 degrees Celsius. And so now I can go ahead and calculate my Q value. So when I plug these into my calculator, I get something like 100 times 2.09 times 10. And I get a value for the heat that is put in to be 2,090 joules. Oops. just joules. So that's my first calculation. Then I need to do my phase calculation, my phase change calculation, which is a stoichiometry calculation. And we are at solid, so we'll come back and grab the right number in a minute. But I'm going to start by setting up 100 grams of water, and I'm going to convert it to moles of water. So in 1 mole of water, I have the molar mass, which is 18.02. And then what I'm going to do is I need to go back, so I'm going to mole. So I'm going to take the 6.01 kilojoules in 1 mole of water. So I'm going to take the 100 divided by 18.02 times 6.01, and I'm going to get a value something like 4 sig figs to be somewhere in the ballpark of 33.35 kilojoules. Okay, so now I've gone and I've taken my ice and I got it up to melting. I calculated the amount of energy required to it completely melt and change into water. Now I need to change it back in, not change it back. Now I need to take the water and raise the temperature to 25 degrees Celsius. So back to another heat calculation, which is mass times specific heat times change in temperature. The mass hasn't changed here, so I have 100 grams of water times the specific heat. Now, so this is liquid water, so I'm going to do this. So I'm going to use 4.18 joules per gram per degree Celsius. And now this time, the change in temperature was initially 0, and finally it was 25. So I'm going to take 25.0 degrees Celsius minus 0.00 degrees Celsius. And I'm going to calculate this out for us. So I'm going to take 100 times 4.18 times 25, and I get something like, let's see, what is it? 10,000. So my Q here is 10,450 joules. Okay. Now the problem is asking me to calculate how much energy is needed to change from ice to water at my different temperature. And what I've done, or what I've been able to do here, is I've been able to calculate the amount of energy needed to raise the temperature, the amount of energy needed to complete the phase change, and the amount of energy required to raise the temperature again. The issue is that the problem wants me to know how much energy is required total, not at the individual steps. And I don't know if you noticed or not, but the units, oops, that's not what I wanted. The units aren't the same. I have joules, I have kilojoules, I have joules. And I guess I don't really care what you convert them to, but the unit of currency in chemistry for energy is usually the kilojoule. So I'm going to convert these to kilojoules. So this one up on top here, I'm going to take the 2090 joules, and I'm going to convert it to kilojoules. So 1 kilojoule is equal to 1,000 joules. And so that gives me a value somewhere in the ballpark of 2.09 kilojoules. And down here, I'm going to take my 10,450 joules, and I'm going to convert it to kilojoules. And that gives me a value somewhere around 10.5 with sig figs because of the 25 degrees Celsius, so it's like 10.5 kilojoules. If you keep it, and we do the sig figs later, it's kind of not important. So now what we're going to do is we are going to add up the 2.09 kilojoules plus the 33.35 kilojoules plus the 10.5 kilojoules. So when we add all that stuff up, let's see, we have 2.09 plus 33.35 plus 10.5. We get something like 45.94. 45.94, but I have 2 decimal places, 2 decimal places, and 1 decimal place, so it really becomes 45.9 kilojoules of energy required to raise the temperature, or to raise the ice from -10 to 25 degrees Celsius. All right, we have one more example to go through, which is just a little bit more complicated. Not too much. It's just maybe a little bit longer. So this one, again, I'm going to start by drawing a phase diagram. So I'm going to convert 125 grams of acetone at 50 degrees Celsius to acetone vapor at 65 degrees Celsius. So in my head, I'm not starting with solid acetone. So I'm starting somewhere at liquid. So I'm not going to start all the way at the bottom. I'm going to start like somewhere here where I might be at a liquid already. I'm just going to say this is 50 degrees Celsius. So I'm going to start here, and we have to raise it to eventually evaporate it. So it goes up, we go to evaporating, and then we go up a little bit more, because when I look at the, let's see, the boiling point, which is basically the evaporation point, that's at 56 degrees Celsius. So if we start at 50, we are below the boiling point, so it's a liquid. And we end at 65, that's above the boiling point, so, which is right down here of acetone, right? So that tells me that we are at a gas. So we're going to go from a liquid to a gas, and we have to go through that the heat of fusion phase. I'm sorry, the heat of vaporization phase. So to calculate this out, I'm going to start by raising the calculating the amount of energy required to raise the temperature to the boiling point. So that's going to give me Q is equal to mass times specific heat times change in temperature. Again, the mass is 125 grams of acetone. I see that acetone has a formula of C3H6O. I also know that the specific heat of liquid acetone, which is where we're starting, is 22.2 joules per gram per degree Celsius. So 22.2 joules per gram per degree Celsius. Times the change in temperature. So the initial temperature is 50.6 degrees, and the final temperature in this case is 56.5, because that's the boiling point. 56.5 degrees Celsius minus 50.6 degrees Celsius. So when I go to plug this into my calculator, I'm going to take 125 times 22.2 times 56.5 minus 50.6. And I get a value for the heat to be 16,372.5, which if I look at sig figs, it should be somewhere around 16,400 maybe, or something like that. But we'll come back and we'll change the sig figs a little bit later when we convert it to kilojoules. Or maybe we could just do that now, because why the heck not? So I'm going to convert this joules to kilojoules, because we're going to go to the currency of chemistry. So 16,372.5 joules to kilojoules would be 16.3725. To have 3 sig figs, which is what looks like we need to work with here, we're going to be at somewhere around 16.4 kilojoules. Okay, so now we are going to go from liquid to solid, so we're going to be vaporizing. So I'm going to set up a vaporizing stoichiometry problem by taking 125 grams of acetone, which is C3H6O, and I'm going to convert it to 1 mole of acetone. And so the first thing I need to do is I need to take, let's see, 3 times 12.01 plus 6 times 1.01, which is 6.06, plus oxygen, which is 16. And so that gives me 58.09 grams of acetone. Okay, and then because it's vaporizing, I need to use this relationship here. So that's going to be in 1 mole of acetone, I have 30.2 kilojoules of energy required. So I'm going to take the 125 divided by 58.09 times 30.2, and I get something like 64.95 5 something or another, and because I need to have 3 sig figs, that's gonna end up being something like 65.0 kilojoules. Okay, and so now we have vaporized all 125 grams. So now we're going to go ahead and calculate the amount of heat required to raise it to the 65 degrees Celsius. So again, Q is equal to mass times specific heat times change in temperature. Still 125 grams of acetone, but now we are at a vapor, so we're going to use the specific heat value of 1.47. So 1.47 joules per gram per degree Celsius. And now we need to look at our change in temperature. So our final temperature is 65 degrees, but we were at the boiling point, which was 56. So initially we were 56, the final was 65. So we have 65.0 degrees Celsius minus 56.5 degrees Celsius. So I'm going to take 125 times 1.47 times 65 minus 56.5, and I get something like 1,500. So my Q value is 1,561.875, and that's joules. So we're going to convert that to kilojoules right away. So 1 kilojoule is equal to 1,000 joules, and so I'm going to divide that by 1,000. And I get something like 1.5, 3 sig figs again, 6 kilojoules. So the last thing that we need to do is we need to add all of these things up. So I'm going to take the 16.4 kilojoules plus the 65.0 kilojoules plus the 1.56 kilojoules. So I'm going to take the 16.4 plus 65 plus 1.56, and I get something in the ballpark of 82.96. But 3 sig figs, because of the 1 decimal point, and 2 decimal points, would give me 83.0 kilojoules of energy. All right, so your homework tonight is to do 2 worksheets, the phase change diagram worksheet and the worksheet that comes directly after it, where you are calculating energy changes and phase changes. Good luck, and we'll talk about this on Monday.